So these are some terms that you're going to be hearing a lot about, and I'm hoping to maybe shed some, no pun intended, light on what it all means. So color space. We talk about color space. There are a number of ways of referencing it or displaying it. On the left, we have the 1931 CIE color space. It's also known as a chromaticity diagram. And really, this is what the human eye can perceive. On the outside perimeter of this horseshoe are all the saturated colors. In the middle, you have your white. There's this little curve that runs through the center. It's called the Planckian curve. So all your Kelvin temperature follows that curve. If the color point happens to fall above that line, it turns green or has a green hue. If it's below that, it has a magenta hue. There's also a new version of this chart. It's the 1976 version. And you'll see how it's different where in the green zone versus the red and cyan zones, how they've basically been transposed. And so again, there are two different ways of looking at it. And in terms of, well, I'll have the other presenters get into more detail. But just so we know what we're talking about in terms of color space. Color gamut. Again, this refers to the entire color range available on a particular device. Now, be it a camera, be it a lighting device, a projector, a monitor, a video wall. And so that we all know the term Rex 709. And so that in a display is all the color that it can display. So if your camera is recording outside of that, it's not necessarily, well, flat out, it's not going to show show anything that's outside of Rec 709. And all of these various devices may not actually have the same gamut. So things start to gain a little more complexity as we go. So some of the more common color gamuts that we're all familiar with, Rec 709. We've got P3, it's a color space for digital projection. 2020. There's a lot of talk about 2020, especially when it comes to video walls, trying to get into that color space of 2020. What you'll find a lot of references to near 2020, near P3. And usually that is because it's really hard to hit those greens. The cost of an LED to render that color point at the extreme edge of that color space is exceedingly difficult. It has very low yield. As a consequence, is very expensive. And then we have the all-encompassing ACEs, which there'll be some explanation, I believe, on ACEs from one of the other presenters. Now, one of the interesting things was camera response. Now, we've done a lot of research on trying to model cameras, and we do know that they see light differently. Now, you never really apply a response or talk about a camera response as a gamut. We don't do that. For that reason, you won't find anything online that refers to camera gamut. But since we know the response of the camera, you could actually plot it much the way you would a gamut. So we went through this exercise just for the sake of curiosity. So in no particular order between these four cameras, this is sort of what they look like. So again, it's of academic interest because ultimately whatever gets outputted is going to be in an output gamut that is going to be displayed. So that gives you a little preface into where we're going. Another term that you may hear quite often, it's pronounced different ways. Metamerism, potato, potato, tomato, tomato. Again, as it pertains to cinema lighting. Now, so metamerism, that's how I call it, refers to the fact that colors can appear different depending on the spectral makeup of the light source, which is further complicated by the varying camera response characteristics. So again, we build complexity on complexity. There is no easy answers or no easy solution to a lot of the challenges that we have, but understanding where the challenge lies maybe helps us better direct how we approach it in the first place. So there are all these different ways of characterizing a light. And what has frustrated many is to say, well, listen, I dialed 3200 on this light. I dialed 3200 on that light. And I did the same on these other units, yet none of them match up. Welcome to metamerism. It's just the way it is. Because they all have different ways of displaying their spectrum. And mathematically, they're absolutely dead on correct. That is the right number, but spectrally doesn't match the other stuff.